And hello there and welcome. We're looking at the derivative and limits today in our Math 221 course. First up, we're going to look at the derivative. The slope formula for a function y equals f of x denoted y equals f prime of x. That's our definition for a derivative. An example of this would be given the function f of x equals x cubed. The derivative is f prime of x, which equals 3x squared. Another definition that we'll want to look at is that of differentiation. That's just the process of computing a derivative. We're not going to give an example of this time since we don't know how to compute derivatives, but don't you worry because we'll soon be able to do basic differentiation in your sleep. So here are a few rules to begin with. Differentiation examples. Derivative of a linear function. So if f of x equals m, which is the slope, mx plus b, then we have that the derivative equals m. So just note that the derivative equals the slope. That's very important to us to note that the derivative equals the slope. That's the slope. Constant rule, the derivative of a constant function, f of x equals some constant b, that derivative is 0. That is, f prime of x equals 0, meaning that the slope of a constant function is 0. Next, if f of x equals x squared, then its derivative is the function 2x. That is, f prime of x equals 2x, and we'll discuss why in just a moment. Another one, if f of x equals x cubed, then the derivative is 3x squared. That is, f prime of x equals 3x squared. Again, we'll look at that in just a moment. So we have this power rule. Let r be any number, and let f of x be equal to x to the r, and remember r is a number. The derivative f prime of x equals r x raised to the r minus 1. So we were looking at f of x equals x squared. In this case, our r was 2. And we said that f prime of x was equal to, bring down your exponent, x to the, and then just do your r minus 1. So 2 minus 1 is 1. So that's why the derivative of x squared is 2x. We also looked at in our previous slide this one. So let's look at what f prime of x would be equal to. So we looked at f of x equals x cubed, and the derivative of f of x is bring down your exponent and then do 3 minus 1, which would be 2. So we call that a power drop rule. So we're going to be using that a lot. So let's look at this function. F of x is 1 over the 7th root of x. That doesn't fall into any of our little power drop rule that we just looked at. Here's our given equation, but we can rewrite it a little bit. Let's rewrite the denominator as an exponent. This is going to be key to any time you have a radical. Now I'm still not there yet, but if I rewrite it again using a negative exponent, hey, I've got something where I can bring down that exponent, negative 1/7, bring it on down, and then I'll do negative 1/7 minus 1. Got to get a common denominator for that. So my answer is then negative 1/7 x to the negative 8 over 7. So this would be my answer. Now what we've done so far has been for the sole purpose of rewriting that function so that we could get it. That's why we did all of that rewriting, is just to get it in the form x to the r. And we used that power rule where r was negative 1/7, and then we just simplified. So let's play this again. We need to find the slope of the curve at y equals x to the fifth at x equals -2. So first up, what we're going to do is we need to find the derivative of the function. So we write it as f of x equals x to the fifth. We find that derivative using the power rule, and we find that f prime of x equals 5, x to the fourth, sorry. So since the derivative function yields information about the slope of the original function, we can now use f prime of x to determine the slope of the original function at x equals -2. So what we're going to do is say the derivative is the slope. So since we found the derivative, we can just plop in a -2. F prime of -2 equals 5 times -2 raised to the fourth. And then just computing that, f prime of -2 is 5 times 16, which is then in turn 80. And we have found the slope of the curve at x equals -2. All right, here's the equation of a tangent line. Now this is just my regular equation, point slope formula. Notice normally I would write y minus y1 equals m times x minus x1. That's what I would normally write. This f of a is just our y1, so y minus f of a equals f prime of a, which is just our slope, and all times the quantity x minus a, where a is our x1. So let's find an equation of a tangent line here. So f prime of x equals plain old f of x, equals 3x at x equals 4. First, we're going to find the derivative of the given function. We write down our function, f of x equals 3x. This is our given function. We find our derivative, f prime of x equals 3. We have differentiated. Notice that in this case, the derivative function is a constant function, 3. Therefore, at x equals 4 or any other value, the value of the derivative will be 3. So we are going to write down our equation of the tangent line, inputting for our x equals 4, y minus f of 4 equals f prime of 4 times the quantity x minus 4. Plugging those values in, y minus 12 equals 3 times x minus 4. Since f of 4 equals 12 and f prime of x equals 3, we can just simplify, and we have y equals 3x, and that's the equation of the tangent line to that graph. Now, sometimes we're going to use a different notation, and sometimes it's convenient. We use the Leibniz notation for derivatives. Means exactly the same thing. We're going to do exactly what we were doing before. The operation of forming a derivative, f prime of x, from a function f of x is also indicated by the symbol d over dx. This is red, the derivative with respect to x. Thus, we can just say the derivative with respect to x of f of x equals f prime of x. Now, for example, if I'm going to take the derivative of x to the 6 with respect to x, I drop my 6 and subtract 1, and I get 6x to the 5th. Next example, derivative of x to the 5/3 with respect to x is going to be drop your 5/3, subtract off 1 from 5/3, and I'll get 2/3. So 5/3 x to the 2/3. The derivative of 1 over x with respect to x, I could say that that is x to the -1. I'm going to drop my -1, subtracting off. I would get -1 times x minus 1, and that's how I get that -2 and simplify to the -1 over x squared. When working with an equation of the form y equals f of x, we often write the derivative of y with respect to x as a symbol for the derivative f prime of x. So you can write either one. For example, if y equals x to the 6, we could write it like that. Or we could write y prime equals, or we could write f prime of x equals. You will see all of those notations. Ultimately, we're going to like this notation. It's better and it's more effective notation for working with derivatives, but you can see all of those, and I will interpret those as such. Now, limits in the secant line calculation of the derivative. We're going to be looking at the difference quotient, and that is f of x plus h minus f of x all over h. Calculating the derivative informally, we could calculate f prime of x by simply writing the difference quotient, this f of x plus h minus f of x all over h, for h not equal to 0. Simplify this difference quotient and then let h approach 0, and the quantity that is our difference quotient will approach f prime of x. So we have a graph of just a simple curve that is going up. I picked 2 points, one at x and one that's a little greater at x plus h. So the first point P at x we have, and then the next point Q at x plus h. The slope of that secant line, which is the line that goes through to both of those 2 points, is what we are talking about when we're talking about the difference quotient. You're going to have a few problems like this. So on this slide, we're looking at limits in the secant line calculation of the derivative, and what I wanted to do is just show you how to work the homework problems that deal with the difference quotient, which is f of x plus h minus f of x all over h. The questions will be something of the form, I just copied one here. Compute the difference quotient for the function f of x equals 2x squared. It'll be any number of functions there. And this is just the one that I selected to work for you guys. So first thing I would do would be to write that difference quotient out. And next I would substitute in for the x plus h. Now notice here that we have, this x plus h quantity squared. And what I've done is just replaced x with x plus h and then subtracted off my f of x here. Moving forward with it, I multiplied out the x plus h quantity squared, and that would be the x squared plus 2xh plus h squared when you multiply all of that out. That was all that I did for that step. Then I distributed my 2, and I have 2x squared plus 4xh plus 2h squared minus 2x squared. Notice that my 2x squareds will cancel out, and what I'll have left is 4xh plus 2h squared all over h. I notice that numerator has an h in both terms. So I'll factor out that h, and note that my h will cancel, leaving me with 4x plus 2h. And this will be, you'll have a handful of problems, or you'll have to use this difference quotient. Some of them will be messier than others. If you have to put it to the third power or something, it does get a little messy. But if you need help with it, just send me an email and I will work through any of these problems with you. And if you need help in a live setting, we can do a collaborate. Just let me know how I can help you, and y'all have a wonderful day.